If f of x, y has a maximum or minimum subject to the constraint g of x, y equals 0, then it will occur at one of the critical numbers of the function capital F, defined by f of x, y, and lambda, and that's going to be equal to the function given f of x, y minus lambda times your constraint. The constraint will be a function also of x, y that was set equal to 0. Lambda is called a Lagrange multiplier. To find the minimum or maximum of your function f, use the following steps. Step 1, solve the following system of equations. These will be built from your partial derivatives. Capital F, whatever that function is, you'll take the derivative of it with respect to x, y, and lambda, and you'll set all those equal to 0. Step 2, you're going to evaluate your lowercase function f, the one that's given in your problem, at each solution point obtained in step 1. The greatest value yields the maximum of f subject to the constraint g of xy equals 0, and the least value yields the minimum. Economists call the Lagrange multiplier in a production function the marginal productivity of money. We'll also look at an example soon that involves a Cobb-Douglas function. Use Lagrange multipliers to find the indicated extrema that's indicated. First, we're asked to maximize the function f of xy equals x times y, subject to the constraint x plus 2y minus 4 equals 0. You want to make sure that your function g of xy is set equal to 0. In this problem, it is. Next, we're going to write capital F. That's going to be our function involving both the original function lowercase f and the constraint g. Capital F of xy lambda is defined as lowercase function of xy. In our problem, that's x times y, minus lambda times the constraint, and that's the part that is set equal to 0, x plus 2y minus 4. That goes in here right after the lambda, so lambda times x plus 2y minus 4. After distributing the lambda, we get xy minus lambda x minus 2 lambda y plus, because of the two negatives, plus 4 lambda. Taking partial derivatives with respect to x first, we get the first term with the derivative with respect to x gives us y minus lambda. The third and fourth terms have no x, so there's no derivative to take. It's derivative of 0. So we have y minus lambda equals 0. Now we go through, take our partial derivative with respect to y. We have, starting with the first term, that's going to be x 0 minus 2 lambda and 0, giving us x minus 2 lambda equals 0. Taking the derivative of that function one more time, but with respect to lambda, we get 0 minus x minus 2y plus 0. Well, no, plus 4, excuse me. That also, there's three terms with lambda. Negative x minus 2y plus 4, and we'll set that equal to 0. Once you have your partial derivatives taken and you set those equal to 0, that forms a system of equations that we need to try and solve. After this, the next step is to solve for lambda in the first equation. So go back up to f sub x, that derivative. Solving for lambda, you get lambda equals y. And that, again, that's from this first line. Solving for lambda, you get lambda equals y. Then you go to your second equation, replace, you substitute that into lambda of the second equation, and you can either solve for x or y. So we're going to replace lambda with y, x minus 2y. Decide which one of those two terms is easier to solve for. In my opinion, it's easier to solve for x. You add 2y to both sides. So x is equal to 2y. Now, substitute your big function f, the capital F, and solve. So back up here, we had capital F was our function, the one that we took all the partial derivatives from. let's take that and then we're going to substitute x as 2y. So right here we had a negative x, that x gets replaced with 2y. Then we have minus 2y plus 4. What it does is it gets us out of a 2-variable trap and puts us in 1 variable only. That totals negative 4y. If we solve for y, subtract 4, divide by negative 4, we get y equals positive 1. Going back to the step above where we have this little purple highlight, since x is equal to 2 times y, and we just figured out y, x has to be 2. That gives us an ordered pair xy of 2 and 1. Finally, we substitute this point back into the very original function we're supposed to maximize, lowercase f xy, which is defined as x times y. So at the very end, we take our function given, plug in 2 and 1 for x and y respectively. X times y gives us 2, and that's our maximum value. Using another function, same idea, we're going to use Lagrange multipliers to find the indicated extrema. We're going to minimize this function using this constraint. Now this constraint is not set equal to 0, so the first order of business is to add 17, get all your terms on one side, and then these 3 terms will be your g of x, y. So keep in the back of your mind, you need to make sure your constraint is first put equal to 0 before you identify your constraint function g. Now we'll write a capital F function. Capital F is defined as the original function given, x squared plus y squared, minus lambda times our constraint. We just found our constraint, so minus lambda times our constraint. Distributing lambda, that gives us x squared plus y squared plus 2 lambda x plus 8 lambda y minus 17 lambda. Taking partial derivatives with respect to x, y, and lambda, starting with capital F, starting with x terms, we have 2x, 0, 2 lambda, 0, and 0. There's only 2 terms that have an x, so we have 2x plus 2 lambda equals 0. Partial derivative with respect to y, we'll have 0, 2y, 0, 8 lambda, plus 0. There's only 2 terms with y, and those derivatives are 2y and 8 lambda. Set that equal to 0. And then go back through a third time, take the derivative of your terms involving lambda. So we'll have 0, 0, 2x, 8y, and minus 17. There's 3 terms with a lambda, so there will be 3 terms in your partial derivative. Solve for lambda in the first partial derivative. So we'll take our first line. In order for that to be equal, lambda has to be equal to negative x. Substituting that into the second partial derivative, we have 2y plus 8 lambda, but you trade your lambda out for a negative x. Simplify, that's 2y minus 8x equals 0. Pick either x or y, whichever one you think is easier to solve. I'm going to add 8 x's, divide by 2, and that gives me y equals 4x. Now, go back into your capital F of lambda like we did on the last problem, this equation right here, and substitute in your y as a 4x. So we're going to get 2x plus 8y, the y trades out for 4x, minus 17 equals 0. Solving for x, we get x equals 1/2. After you figure out what x is, you go right back to the step above. If we plug 1/2 in for x, then that tells us y has to be 4 times the half, which is 2, giving us the ordered pair 1/2 and 2. X value first, y value second. Now, once you've figured out the point where the extrema occurs, we go all the way back up. The original function we were given and asked to minimize was x squared plus y squared. We're going to replace x and y in that original function with 1/2 and 2. So that's 1/2 squared plus 2 squared. Let me darken the ink up a little in here. That's a little hard to read, but that's 1/2 and that's a square. When the dust settles and you've made your calculation, you should get 17/4. And that minimizes the function in the beginning of the problem subject to the constraint given second. This next function is called a Cobb-Douglas function. You see it a lot in your economics classes. The production function for a manufacturer is given by function f of xy as 100 x to the 0.25 power times y to the 0.75 power, where x is the number of units of labor at $60 per unit, and y is the number of units of capital at $48 per unit. The total cost for labor and capital cannot exceed $100,000. So we're going to write our constraint. X is for labor, $60 per unit of labor, plus $48 per unit of capital, and we're going to set that equal to 100,000. That's the max we're allowed to spend. Because this constraint is not set equal to 0, we got to move the 100 grand over, so that's going to be subtracting 100,000 on both sides. This is our constraint. This is what we call lowercase g of xy. The original function given, we're going to use it and the constraint we just found and write our capital F function in terms of x, y, and lambda. When we do that, we take our original function given, so that's 100 x to the 0.25 power times y to the 0.75 power, minus lambda times our constraint. That's the first thing we did. Distributing negative lambda to all three terms, we get capital F equals the original function given minus 60 lambda x minus 48 lambda y plus 100,000 lambda. Now taking our partial derivatives of this big function, be very careful here. 0.25 times 100 is 25. Subtract 1 from your power, that's negative 0.75. The y term will be, the y part of it, leave it alone. We're only concentrating on the x parts. Second term, derivative negative 60 lambda. The third and fourth terms have no x, so their derivatives are 0. This is the partial derivative with respect to x set equal to 0. Now we go back, capital F with taking the derivative with respect to y. 100 times 0.75 is 75. Take 1 off the power, that leaves a negative 0.25. The x part of it stays the same. Second term has no y. Third term does. Its derivative is negative 48 lambda. Fourth term has no y, so its derivative is 0. This second line is the derivative with respect to y set equal to 0. And then finally we go back through taking the derivative with respect to lambda. This initial function has no lambda, so the derivative is 0. Second term derivative is negative 60. Third term, with respect to lambda, our derivative is negative 48y. Fourth term derivative is 100,000. We'll set that equal to 0. Now we have all three partial derivatives. Let's take our first partial derivative, solve it for lambda. Let me get this inked in better. There we go. So we take our first partial derivative, the one with respect to x, solve it for lambda. I'm going to add 60 lambdas to both sides, and that essentially moves it over and changes the sign. That's really the fast way to think about it. Dividing both sides by 60, 25 over 60 reduces to 5/12. Our powers remain the same. Now, go to your second partial derivative, replace lambda with this 5/12 term that we just found. So that's 75xy, that all stays the same, minus 48. Now this lambda up here is the one we replace with this lambda that's in terms of x and y. Solving for lambda, excuse me, I've already done that. It's easy to get lost in mid-problem too. Let me make that look a little better. That's supposed to be a 7. No, actually it's supposed to be a 2. Let me erase that. Sometimes when these convert to PDFs, they don't translate very well. All right, let's get it together. We're almost done with it. So the second partial derivative, we had 75 x to the 0.25, y to the negative 0.25, minus 48 lambda. So I'm going to substitute this in for lambda. 48 times 5/12 is 20. So this is where this 20 is coming from. In order to try and get rid of all these nasty powers that are decimals, like that's a 1/4, that's a -4th, the best way to do it is to take your smallest power from the x terms, make it positive, because whenever you multiply through, you're going to add your exponents. Well, we want to eliminate a negative 0.75. It's the smallest. As far as your powers of y go, the smallest one is the negative 0.25. So I'm going to get rid of it by multiplying by a positive 0.25. So I'm going to multiply both sides of this equation by x to the 0.75 times y to the 0.25. Trust the process. On the right, 0 times our multiplier, that goes to 0. On the left side, when we multiply the first term, we're going to get 75. 0.75 plus 0.25 is 1, so that's going to give us x to the first. The y's, because they're opposites, will add up to 0, and that eliminates the variable y. On the second jump through in distributive property, we're going to have negative 20. X to the 0.75 plus negative 0.75 makes the x's add up to 0, so that's why there's no x anymore. Y to the 0.25 plus 0.75 makes it y to the first. So if you're careful when you multiply both sides, you can eliminate all your fractions and or decimal exponents. Let's solve this for y. Add 20 y's to both sides. That'll give you 75x equals 20y. I'm going to write that in actually. Divide both sides by 20, and that'll give you y equals, reduce your fraction, 15/4 x. So y is equal to 15/4 x. On the next page, we're going to finish this up. So remember that y equals 15/4 x. Substitute back on the last page your third partial derivative, the one that was with respect to lambda. So we have negative 60x minus 48. That was our y value that we found at the very end, plus 100,000 equals 0. 48 times 15/4 is 180. So that gives us negative 60x minus 180x plus 100,000. The first two terms make negative 240x. Subtract 100,000 on both sides. Divide both sides by negative 240. And that gives you a reduced fraction of 1250 over 3. Since y was equal to 15 over 4 times x, this is our x value, 1250 over 3, y will come out to reduced 3125 over 2. Back in the original problem, your lowercase f, we substitute in the 1250 over 3, that was our x value, and our y value was 3125 over 2. Plug that into the original function. Be very careful when you're putting these exponents in your calculator. So we'll have 100 times our x value to the 0.25 power times our y value to the 0.75 power. When the dust settles to the nearest whole number, and that's the way WebAssign wants it, is to the nearest whole number, it's 112,283 units. The rest of the information is about the final exam, but if you're looking at this, you don't have to take that final exam. This is from a previous semester.